math popularizers would describe these as self-avoiding space-filling curves. It turns out there's two problems with that idea. Problem one, there's no such thing as a self-avoiding space-filling curve. And the other problem, whoa, what's going on here? Oh, I thought you were an earthquake. I'm from California. So the other problem is these things aren't space-filling curves in any sense. So these bottom three, these are naughty, nasty, self-touching, quote-unquote, space-filling curves. In fact, they are exactly the same space-filling function, just sampled differently. So what does a space-filling curve really look like? It looks like a solid blob. That's what it means to fill space. So I have a slogan, which is, if you don't have the function, you don't have the fractal. And to just exhibit that, let's ask a really simple question about the fractal. About a dragon, when its most basic property is it's two dragons connected end to end. You can see the blue one and the pinkish one here. Okay, and it's clear that they connect at the halfway point. In other words, this is 0, this is 1, this is a half plus a half I. But where is the other end of this region of shared boundary? Well, it turns out that it is 2/5 plus I over 5. Now, how could that possibly be on the dragon? Because we're taught that dragons are made out of dyadic rationals. Well, we shouldn't be taught that, okay? And in fact, the dragon is a map from 0 to 1, and when we get to 3/7 and we get to 5/7, we come to this magic junction point right here both times. So, how in the world can we assign values to dragon of 3/7 and dragon of 5/7? We can do so because of this kid who was at G4G9, and his name is Julian Ziegler Hunts, and he's a freaking genius. Okay, and he wrote a 6-line function called Piecewise recursive fractal. And it calls itself in 3 places, redefines itself twice, has no termination condition, and is the most inscrutable piece of code you would ever want to look at. I consider it basically self-aware. In other words, the idea is that it's circularly defined in some sense, and yet there's no end check. And what it really does is it lists all of the things it's working on. It's all these recursions that are unsatisfied until it finds 2 of them. And it's able to solve that. It's able to imagine that the map from one to the other has a fixed point, and it solves an equation for that fixed point and artificially redefines itself at that point. And so it mentions its name so many times that if it were shorter than piecewise recursive fractal, it would be a much smaller function. So let's do a little bit of something here. So anyway, if we now evaluate this dragon function, you'll also notice that it's spelled D-R-A-G-U-M. And the reason for that is that this thing, incredibly enough, can do the inverse as well. So there's an undrag as well as a dragon. And if we run dragon on just unit fractions, powers of 2, then it's an identity function. If we run it over the 1 over 1/7, 2/7, 3/7, 4/7, 5/7, 6/7, you can see those red figures there are the 2 magic places where that loop closes on the, I'm sorry, I showed you back here. Yeah, right here. So now, what are we doing? It turns out I was able to evaluate the dragon function at some of these crazy theta constants. So this is the first time I've ever seen a connection between fractal type mathematical constants and good old-fashioned 19th century special function values. And there's a lot of these. They'd be hard as heck to prove, but I think I know how to do it. These were found more or less empirically, but I'll bet you anything they're right. So then here's my claim that this thing has an inverse. Namely, here's this thing with these 2 red values here. if I run the inverse function, undrag, over those values, you'll notice I get 3/7 and 5/7 together as the inverses, and it appears twice. So now here's undrag of 1/6 plus I over 3. It's a triple point. Okay, so not only do space-filling functions hit all of the points, they have an uncountable number of double points and countably infinite triple points. So here's a triple point of the dragon function right here. So now let's go a little further. Remember down here was our magic point. You'll notice that if you have a double point, that's a loop, okay, because you start and end at the same place. So in fact, the actual function loops and it invades both halves, like so. Now, it turns out, this is an example of a triple point. Okay, now there's uncountably many, there's countably infinity of, it's dense, that's what I want to say. This dragon curve is dense with triple points. And, I guess that's all we need to say about it. But I just colored it, 4 different colors, and there's this place where all 4 come together, and that is, by golly, a triple point. So now, one thing to note where we're on this page, what a dragon looks like is it's a spiraling sequence of larger and larger blobs, and then suddenly they start getting smaller and spiral the other way. Now, there isn't any particular reason why they have to do that. So there's a space-filling function which never stops enlarging and spiraling. And it's it's simpler in some sense than a dragon, in the sense that a ray, an infinitely long ray, is simpler than a line segment, because a line segment is complicated by having 2 ends, and a ray is simpler by having 1 end. So now if we take 2 dragons and reverse 1 end for end and union them or intersect them, then this lower purple plus red thing is a dragon, and the other end is also this blue plus purple is another dragon, and that's kind of interesting. But it turns out that this picture is exactly what you would get by just putting together 4 dragons in this fashion. So, here's an example of a dragon that I was trying to get a picture of it going on forever, but of course, forever is more than memory I can afford. And so now, here's another interesting, simple question that you can ask about dragons. Namely, what is the longest line segment that you can inscribe in a dragon? And it turns out to be √2 long. It turns out that it's dense with triple points. And the interesting question is, for instance, how many places does it touch the boundary? It turns out that here it appears to be touching once. That is a Cantor set. That's an infinite number of touches right there. So this is a really weird thing that you'd have to zoom in to demonstrate. And then here are, I've never seen this phenomenon. At any rate, if I change colors when I revisit a triple point, I get this effect. So I see all the triple points lined up. And here I was attempting to draw a perspective view of an infinite one that didn't work exactly. Okay, so the dimension of, in some sense there's 2 fractals in a dragon. Namely, there's the fractal 2-dimensional fill, and there's the 1.5 dimensional skin. And
Bill, we're running over in time.
Wow. Okay, let me see if I can just skip to. Okay, well here's a. Okay,
time
so
for one more.
All right, that'll do, I guess. But believe it or not, wow, that is not hidden line. That just happens. Okay, when you know the recursion. Okay, well, thank you.